Okay, let's look at another one here. Example, approximate the cosine of 1.7. Now this one we're going to have to round to 3 decimal places. Okay, let's check it out. Obviously, guys, back in the old days, they needed to take trig values of all kinds of radian measures that weren't pretty, right? They just do it at pi over 4 and pi over 3. They might have something like the cosine of 1.7. So we need a good approximation. Okay, we can get this with our linearization. So I'm just going to write down that formula again. L of x equals f of a plus f prime of a times x minus a. And now we're going to think, all right, we need a function. We need to recognize what x equals, and then we need to figure out an easy value that's near that x that we could plug into our function. All right, well, what is the function? What is f of x? Well, we're looking at cosine 1.7. Let's make f of x cosine x. That's a good idea. What is the x value? Well, of course, it's 1.7. And now here comes a tricky part and why I picked this example. What is an easy value near 1.7 that we could put into cosine? You're like, well, wait a second, I don't know. Well, the easy, if you will, things, the things we know that we can put into cosine are those pi, fractions, right? Pi over 2, pi over 3, pi over 6, pi over 4, pi itself, right? Which of those is near 1.7? You think, well, it's not pi because pi is 3.14. Well, is it pi? Maybe pi over 2. And yes, that's it. That's as close as we can get with something that we know right away. So we're going to pick A as pi over 2. Pi over 2 is, 1.57, 0.8. Okay, I'll just stop there. Yeah, we got it. That's fine. So that is near. We want the exact value, obviously, but we know it's near this. It's as close as we can get. Okay, so let's keep going. Let's fill in all the parts. So I know A is pi over 2. What's f of A? Well, let's put it in. Our function at pi over 2, cosine pi over 2, as you may know, is 0. If you want to use a calculator for that, I got no problem there. All right. Hey, we're going to need the derivative. Well, f prime of x here is negative sine x. Okay. And we're going to have to plug that a value into that as well. F prime pi over 2, negative sine pi over 2. Well, sine pi over 2 is 1. So we've got negative 1. And now we're all set. We can plug in for f of a, f prime of a, and a. And here's our linearization of cosine x at pi over 2. All right, 0 minus 1 times the quantity x minus pi over 2. Because we have the 0 in this case and also the negative 1, I'm going to clean this up just a little bit. Maybe we just call it L of x equals negative parentheses x minus pi over 2. It looks a little bit nicer. Okay, and remember that all that is the equation of the tangent line at that point. We're almost there. For our answer, grab your calculator and plug in x equals 1.7. And this one we're rounding to 3 decimal places. Again, this is something that we could do by hand if we really wanted to. We could get pi over 2 to 3 decimal places, and we could, subtract and whatever. We're not going to bother with that tedious work. Here we got negative 0.129 when we plug in. So there's our answer. We're done. If we were living back in the old days, we'd say, okay, I'm just going to trust this procedure that really is close to the cosine of 1.7. And we would probably have a pretty good idea that it is very close. But since we live in 2020, let's compare that with what modern technology would say. Cosine, make sure you're in radians, cosine 1.7. What are we going to get? And you got to be kidding me. This is so close. Look at that. Negative 0.1288. I mean, when we rounded, this is so I forget what it was before you round when you plug in 1.7, but when you round, we just consider that. This is off by, I mean, the 8 here. What is that? 10 hundredths, thousandths, 10 thousandths? That is unbelievable. Pretty sweet. To get an even better idea, I mean, this is pretty powerful just looking at those numbers. But if you want to actually see the graph, you know, in the true scaling, you could graph cosine x and then graph this linearization into Desmos, graph both of them, and then zoom in by 1.7 and just see how close those lines are. And you got to keep zooming for quite a little while before you can really visually separate the equation, the tangent line from the original graph is pretty sweet. Okay. And yeah, I said it here again, like unbelievable. All right. Before we move on, here's a good discussion. Excuse me. Here's a good discussion to have. And this would have been very, very helpful for guys back in the old days. But certainly for us too doing this. Can we tell if an approximation is bigger or smaller than the actual value? Right? Obviously without modern technology or even graphing with technology. Can we tell if an approximation is bigger or smaller than the actual value? And we had one of each. That first example we did, the approximation was actually a little bit bigger. The second example we did, the approximation was a little bit smaller. Can we tell that, you know, without punching those numbers into a calculator? Okay. Yes, we can. And we don't, it's going to rely on a sketch of the graph. We don't need technology to graph this stuff for us. If we have an idea of the graph, then we can tell this easily. Okay, let's look at the first example we did. I'll just show you all of my notes here. For the square root of 4.37, if we graph the function square root x, right? So f of x equals the square root of x. And there's 4. We know we're going to use that, and we know 4.37 is over here. All right. When we draw that tangent line, we can immediately tell that the tangent line is above the curve, right? The tangent line comes and sits on top of the curve like that. So because the tangent line is on top of the curve, the y value we're going to find is on top of the actual y value. Our approximation is actually a little bit bigger than the actual value that we're approximating. The tangent line is above, so the approximation is a little bit bigger. We don't have to have a perfect sketch of that. We don't need to know what these numbers are, right? It doesn't have to be scaled correctly. We can tell that tangent line is sitting on top. It's above. Versus the cosine example. So in cosine, we can just get a rough sketch of cosine, right? Pi over 2, there's pi right there. Okay. Here's 1.7, somewhere in between. I think it's actually probably a little bit closer to pi over 2 than what I'm showing. If we graph the tangent line there at pi over 2, and the way this works, the tangent line sort of cuts through right there. Right, just the way that, because it curves back the other direction, it passes through. Well, at the point in question, right, there's the actual cosine of 1.7. But here's what we found with our approximation down here. In the point in question, the tangent line is below the graph of cosine x. So we know the approximation is smaller. It dropped down beneath, so our approximation is a little bit smaller than the actual. Now, if we were living in the old days, how much smaller? Well, we wouldn't know that. But at least we'd know we're a little bit below what it should have been, if that would be helpful in any way. Okay, we're going to stop this video here. It's differentials next.